This video is about chemical equilibrium. How do we define what a chemical equilibrium is, or a system in chemical equilibrium? All right, so first off, chemical equilibrium. What is this? Well, to understand what a chemical equilibrium is, we have to realize that there are reversible reactions. So many reactions are actually considered reversible, okay? And what that means is that they may not only proceed, as we might expect, like this, from reactants to products, reactants turning into products, what we conventionally think of as happening in a chemical reaction, but they might also instead go backwards, okay? So the extent to which they go backwards is dependent on the nature of the system, meaning like on the chemicals themselves, and on the conditions of the system, and so we'll examine this. But the notation we might use to indicate a system at equilibrium or a reversible reaction would be this right here. And the main new symbol for you is that double arrow in the middle. Okay, so this double arrow, an arrow with half an arrowhead going either direction, or two separate arrows going in opposite directions, that's the symbol for a reversible reaction. So what we're talking about here moving forward is that these types of reactions, or these types of chemical systems, are able to establish what we would refer to as an equilibrium state, or a chemical equilibrium. So we'll learn about that next. What does that mean? So what it means for a system to be in equilibrium, okay, is that technically the rate of the forward reaction is equal to the rate of the reverse reaction. So we'll look at what kind of conditions can lead to a chemical equilibrium being established, and what are some features of a system that is at chemical equilibrium. But the most important thing to remember, and the definition of it, is that the rate of the forward reaction is equal to the rate of the reverse reaction. So that means the reactions themselves do not stop occurring. There are still molecules colliding on either side and reacting. But if we look at the reactants and the products respectively, we don't see a change in the relative amounts of the reactants and products. So we'll describe this further. Okay, so for a system at equilibrium, for an equilibrium to be established, it must be in a closed system, first of all. So what does this mean that it has to be in a closed system? It means that no matter can escape from that system. So you can't have any loss of reactants ever. You can't have any loss of products as they're produced ever. Anything that is generated or is there to begin with stays inside the vessel, okay? If you were able to lose bits of product, then what we would see is that the forward reaction would keep on happening to produce more product. Okay, so we'll see how in future lessons how an equilibrium responds to changes that are imposed on it, or stresses that are imposed on it, such as removing product or removing reactant. But we're going to assume that if it's in a state of chemical equilibrium, it's a closed system. Okay, and then other features you should realize about a system that is at equilibrium are as follows. So first of all, equilibrium can be established, or it was established, from either direction. So you could start with all products and they will react and generate reactants, or you could start with all reactants and they will react and generate products. The second thing is that relative amounts, and the key word is relative amounts of reactants and products remain constant. Notice that it does not say that the amount of reactants and the amount of products are the same at equilibrium. Okay, they're not necessarily the same, but respectively, they remain constant and they remain unchanged if an equilibrium is established. Okay. The third feature is that the rate of the forward reaction is equal to the rate of the reverse reaction. We discussed this already. It defines a system at equilibrium. And the fourth one, and this is kind of interesting, is that although the reaction continues in the forward direction and continues in the reverse direction, we see no observable changes in what we would consider the macroscopic properties, or the macroscopic characteristics of the system. In other words, we would see the temperature remain constant, we would see the pressure remain constant if there were a gas involved or gases involved. We would see the color of the system, maybe on macroscopic inspection. We would just see the color remain constant. It can include other things like the conductivity or the pH or any other physical or chemical characteristics of the system that we could observe and measure. They would remain constant for a system that is in equilibrium. We'll examine a couple of graphs that can help you understand what is happening for a system as it approaches and establishes equilibrium. So the first one that's important to look at is a plot of rate versus time. Okay, if we start with, in this case, all reactants and zero products, as you could maybe establish from this. This is what a rate versus time graph would look like as a system establishes equilibrium. You can see that you're slowly going to have the reverse reaction happening faster and faster, and at the same time you're going to have the forward reaction happening slower and slower until finally they're happening at the exact same rate, and this is the point when we would say chemical equilibrium has been established and the rate of the forward is equal to the rate of the reverse. So another important plot to understand that describes a system as it approaches equilibrium is a graph of concentration or of amount or number of moles over time. So what we see in this plot is that, again, we're going to base it on the previous example where we're starting with only reactants and no products, but we would see as that reverse reaction was increasing in rate, we would see more products get produced, and as the forward reaction was decreasing in rate, we would see a decrease in the amount of reactants, and we would see a decrease in the rate of that reaction as it happened. Okay, so eventually, and really the big point of this one is that if you look at the amount of stuff that's there, when equilibrium is established, it's just flat lines, but those lines are not in the exact same position necessarily. They may come together here, and they may have the exact same concentration with that, but that would kind of be purely serendipitous. There is nothing that says they have to have the same amounts. They just have to remain unchanged. So you can see here they remain constant. Okay, so that's the big thing, is that once equilibrium is established, they're constant respectively, the amounts of reactants and products, but they're not necessarily the same. Just over on the side here, I've also shown that this can look like this. So it could look that actually at the point of equilibrium, the amount of product is greater than the amount of reactant at the end, or it could be approached from the other direction here. If you look at what we start with in this case, we start with all the products and we start with zero reactants, and equilibrium is still established. So remember, what controls actually the relative amount of reactants and products at equilibrium like this? What controls that is what the type of reaction is itself, the nature of the reaction, and also some of the conditions of the reaction, particularly temperature, but also things like the pressure and the volume of the system if it involves gases, and things like that. So definitely just appreciate the difference in the appearance of a concentration versus time graph as the system is establishing equilibrium versus what a rate versus time graph looked like. Okay, if you're having a hard time understanding what's really going on for a system in chemical equilibrium, I like to use analogies to try and bring that to life. And the way I tend to think of it is I imagine the reactants and products like two islands. So imagine this is reactant island over here, and this is product island over here. And if we imagine that on reactant island we have 100,000 people that 10,000 people in this case that permanently live there, and on product island we have 1 million people that permanently live there. if you imagine there's a bridge in between the two islands and there's cars constantly traveling back and forth between those two islands, what you would see is that at any given point in time, the population on reactant island will always be 100, will always be 10,000, and the population on product island will always be 1 million. Okay, the travel back and forth is constant. It's happening always. There's always cars traveling back and forth across this bridge. But if you freeze frame and take an instantaneous snapshot at any given point in time, there will always be 10,000 people on this island, and there will always be 1 million people on that island. So that's kind of an analogy I think of for chemical equilibrium, or a system at equilibrium. Hopefully this is helpful for you as well.